It was the winter of 1944. A field mechanic is kneeling in freezing mud at a repair shop near the German border. The sky is low and grey, and the distant thud of an approaching counter-offensive is growing louder. He is not waiting for a supply truck to bring a fresh transmission for the medium tank sitting dead in the slush. He knows that truck is never coming. Instead, he braces his feet against a jagged piece of armor and uses a rusted crowbar to pry a starter motor from a charred wreck. This is the reclamation program in its most desperate form. It is the moment the industrial power of the United States hits a wall, and the survival of a tank crew depends on one man with a wrench. The part he needs actually exists, and 10,000 of them are sitting in a warehouse in Illinois. But a single coding error in a ledger thousands of miles away has made that part invisible. As the mechanic realizes his war depends on a piece of iron lost in a filing cabinet, a fundamental question remains. How did a nation of mechanics manage to build a supply line that spanned the entire globe? To find the answer, we must look back 4 years to a time when the American military had almost nothing to give. In the late 1930s, the Ordnance Department was operating on what Major General Charles M. Wesson called starvation rations. Wesson led a skeleton crew that had spent 20 years living off the leftovers of the Great War. By 1940, the national stockpile of rifle ammunition had dropped to 500 million rounds. That was exactly half of what the Army held at the end of 1919. The military lacked more than just bullets. In 1940, the United States Army possessed only 28 modern tanks. The rest of the fleet was a collection of obsolete relics better suited for a museum than a battlefield. The truck situation was even worse. The Army operated what Wesson called a polyglot fleet of 360 different vehicle models. None of the parts were interchangeable. If a water pump failed on a Dodge truck, you could not use the part from a Chevrolet parked right next to it. Logistics was a heavy anchor, dragging behind every unit. The true crisis arrived in the summer of 1940. After the fall of France, President Franklin D. Roosevelt made a massive gamble. He ordered the transfer of 25% of the entire American ammunition stockpile to Great Britain. In a single day, the domestic cupboard was stripped bare. The existing government arsenals could not possibly fill the void. When Roosevelt commanded his planners to double their numbers, he was demanding a total revolution. He wanted a shift from slow peacetime manufacturing to a high-speed factory system. The arsenal of democracy was born in a state of absolute panic. Ordnance officers like Wesson began stripping machinery from private companies just to keep the government shops running. They were trying to bridge the gap between building a taxicab and building a tank. A single 12-ton light tank required over 14,000 individual pieces. There was no instruction manual for building these at such a massive scale. History often remembers this effort as a smooth rise of assembly lines. In 1940, it was actually a chaotic struggle against decades of neglect. The Army was fighting a war against its own inventory before it ever saw an enemy. They had the tools to build a world, but no way to move it. The transition was a brutal conflict between technical perfection and the need for volume. Wesson and his team were essentially trying to build a plane while it was already in flight. Every decision made in a Washington boardroom was an attempt to ensure that the mechanic in the mud would not need that crowbar. But as the war accelerated, production was only half the battle. The real challenge was the invisible architecture of the supply line itself. By 1941, the question was no longer about building the tanks, but about finding them. Consider an 11 o'clock meeting in a Washington boardroom in 1940. The air was thick with a psychological cloud of frustration. General Harris and his staff were looking at numbers that simply did not work. The cupboard was not just thin, it was empty. The department launched what they called the 3 waves of plant construction. This was a total decentralization of the nation's industrial heart. They moved production away from the coasts and into the cornfields of the Midwest. Building a bullet was easy, but building a machine to survive a blitzkrieg was a different struggle. A military round has to work every single time in a machine gun firing 800 times a minute. This is where a Frankfurt engineer enters the story. He sits at a drafting table, turning decades of specialized knowledge into standardized blueprints. He is not just making a drawing, he is creating a language. His job is to ensure a contractor in Missouri can produce a bullet that works in the Arctic or the Pacific. He was the architect of a new industrial army. This led to the creation of the GOCO system, or government-owned, contractor-operated. The government would build the massive facilities, but they would hand the keys to private firms like Chrysler and Remington. It was a merger of military requirements and private sector speed. By 1941, this program was granted an A1A priority status, the highest possible. The scale was staggering. The Denver plant rose from the ground in only 7 months. It was not just a factory, but a city of 20,000 people with its own railroad, police force, and hospital. But where do you put 41 billion rounds of ammunition? You cannot leave it in coastal warehouses where a single sabotage attempt or a lightning strike could wipe out a year of production. This realization forced a massive migration of the nation's explosives to the interior. They began building igloo depots, which were reinforced concrete structures covered in earth and designed to direct the force of an explosion upward if something went wrong. This is what transformed the American West. Imagine a Navajo depot worker in the high desert of Arizona. He is guiding heavy ammunition crates into one of these sod-covered vaults under a blistering sun. He is part of a silent, sagebrush-covered landscape that has become the most vital real estate on Earth. He is handling the material that, by 1942, would consume 18% of the total copper available in the entire nation. The program was so vast it necessitated the construction of 4 new brass mills just to keep up with the demand for casings. To understand why this mattered, you have to look at the firepower of the new infantry. A single platoon now possessed the fire capacity of an entire Civil War division. Aircraft-mounted machine guns required absolute perfection, as a single defective round could destroy an aircraft in flight. The department was no longer just a supply branch, but a global industrial engine. They had the volume, but they were about to discover that the enemy was moving faster than their blueprints. The era of the juggernaut had begun to understand the scale of the industrial shift that followed the ammunition crisis. We must look back to a patch of Michigan farmland in the winter of 1940. This was the site of the future Detroit tank arsenal, but at the time, the engineers from Chrysler, who were tasked with building it, had never even seen a tank in person. They had to journey to a government arsenal just to pick up nearly 200 pounds of blueprints. Think about what that looked like: a team of automotive designers, used to sedans and station wagons, staring at a literal mountain of paper that described a machine they did not yet understand. This was the beginning of a chaotic collision between two very different industrial cultures. On one side, you had the heavy locomotive builders, like Baldwin and American Locomotive. They were used to bespoke manufacturing, building massive heavy machines one at a time, often by hand. On the other side were the automotive giants who lived and died by the assembly line. The army needed tanks immediately, which led to the creation of the M3, a machine often called the Grant or the Lee. It was a stopgap, a hurried design that was literally riveted together because the industry did not yet have the capacity to weld armor plate at scale. Now, think about what a riveted tank meant for the men inside it. To an engineer, a rivet is just a fastener, but to a tanker, a rivet was a secondary projectile. If a German shell hit the outside of that armor, even if it did not penetrate, the shock could snap the rivets off inside the hull. They would go flying through the cabin like bullets. The locomotive builders were comfortable with this design because it was how they built steam engines, but the automotive engineers knew it was a dead end. They were learning by doing on a massive, terrifying scale, trying to transition to welding and casting while the production lines were already moving. The pressure on these men reached a breaking point in September of 1941. This is the moment where the arsenal of democracy shifted from a plan into a juggernaut. President Roosevelt sat in a meeting with his military planners, his iconic cigarette holder clenched in his teeth, and looked at the production goals they had carefully calculated. Then, he simply commanded them to double it. For officers like General Wesson, this was a moment of pure professional shock. The original goals were already pushing the limits of the nation's steel and rubber supplies. Doubling them meant moving away from conservative, incremental planning and toward a total industrial mobilization that would eventually cannibalize almost every other civilian industry. It forced a design-on-the-fly reality. At one point, officials authorized the production of 1,000 tanks before the final blueprints were even finished. They were building the factory and the vehicle at the exact same time. To understand how desperate this scramble became, look at what was known as the powertrain shuffle. Because of massive bottlenecks in transmissions and final drives, there were days when the industry simply did not have enough working parts to finish the tanks on the line. To keep up appearances for the press and the Secretary of War, a single functional powertrain was sometimes rushed by truck between the assembly lines of different companies. They would install it in a hull, hold a first completion ceremony for the cameras, and then immediately rip the parts back out to send them to the next factory. It was a sequence of industrial theatre meant to hide the fact that the supply chain was screaming under the weight of the directive. But out of this friction, the M4 Sherman was born. It represented the moment the automotive mindset finally took control. The Sherman moved away from the boxy, riveted hulls of the past toward welded armor and a one-piece cast upper hull that the workers nicknamed the inverted bathtub. This was a massive technical breakthrough. By casting the hull as a single piece of steel, they eliminated the need to join over 100 separate components. It was faster to build, it was stronger, and it saved thousands of man-hours of skilled labor that the country did not have to spare. General Harris and the organizational architects began to decentralize this entire process, moving procurement out of the Detroit bottleneck and creating a network of subassembly units. They realized that a tank was not a single machine, but a collection of competing industrial problems. Engines, transmissions, and armor plate were all being manufactured by different firms and forced to converge in one place. By late 1942, the program reached a peak of 4,000 tanks a month. This was the victory of the system over the machine. The United States did not win by building a perfect, invincible tank. They won by creating an industrial organism that could outproduce and out-evolve the enemy's rigid design cycle. They froze the specifications in late 1942 to move from prototype-style construction to true mass production. They chose the good enough in massive quantities over the perfect in small batches. By the time the first Shermans were rolling off the lines in Detroit, the era of the hand-tooled weapon was over. The nation had built a machine that could build the war. No one argued after that. By 1943, the challenge was no longer making the iron, it was finding it. The factories in the Midwest were churning out hulls and shells at a rate that had finally overshot the requirements of the battlefield. Yet at the front, tanks were sitting idle in the mud for want of a single gasket or a specific bolt. This was the era of the deadline vehicle, where a multi-ton machine was rendered a useless paperweight because the part it needed was lost in an administrative fog. The iron was lost in the files. To understand why this happened, we must look back at the administrative landscape of the pre-war military. For decades, the army had purchased equipment in small, uncoordinated batches. This had created what officers called the numbers racket. A single ball bearing, used in 3 different vehicle brands, might carry 5 different manufacturer part numbers, 2 different government drawing numbers, and a separate stock code. If you were a mechanic in the field, you were looking at 260,000 distinct automotive components, managed under 8 different, conflicting numbering systems. The army was blind to its own inventory. Consider the administrative struggle of the men tasked with moving those parts. A clerk at the Rock Island Arsenal sits at a desk late at night under a single lamp. He is surrounded by stacks of ledgers and requisition forms that are already months out of date. His job is to find one specific valve for a heavy truck. But in his files, that valve exists under 4 different names. He is fighting what was known as the paper war, a struggle where the data was often obsolete before it could even be acted upon. If he made a single clerical error, 10,000 units of the wrong part might be shipped to a port in New Jersey, while the right parts sat forgotten in a warehouse in Georgia. A misplaced pencil stroke halted a division. This was not just a failure of bookkeeping, it was a strategic bottleneck. By late 1942, the Central Stock Control Office was so overwhelmed that it was months behind on posting distribution cards. The inventory data was effectively useless. To break this stalemate, General Harris and the organizational planners realized they had to move away from manual ledgers and toward the cutting edge of industrial management. The inventory existed only on paper. This brought the introduction of punch card technology to the military. Inside a machine records unit, an IBM operator spends her shift feeding stacks of MasterCards into a high-speed electrical accounting machine. She is translating the physical reality of the warehouse into a new language of 11-digit alphanumeric codes. Every bolt, spring, and catch is assigned a unique identity that bypasses the proprietary manufacturer numbers. This was the birth of Science Industry Ordnance Management. It was the realization that in total war, the paper trail is as vital as the production line. The punch card became a weapon of war. But the transition was painful. When the Supply Control Office was forced to move to Detroit in late 1942 to be closer to the automotive plants, the system nearly collapsed. The office lost half of its experienced engineers, who either took commissions or jumped to the private sector for higher wages. The remaining staff suffered from what they called the Aleutian stare of administration. a deep psychological exhaustion born of being constantly harassed for inefficiency while their resources were slashed. They were trying to reconcile 17,000 backordered items, only to discover through high-tension investigations that many of these shortages did not actually exist. They were simply record errors. The parts were in the bins. The ledgers just could not find them. The ledgers could not find the steel. General Harris pushed for a radical decentralization to fix this. He helped implement the product center model, where specific locations took total responsibility for a single class of material. The Rock Island Arsenal took over mobile artillery, while other sites managed fire control or small arms. This reduced the number of items any one office had to track, cutting the time to consolidate reports from 6 weeks down to 2. The wait dropped from weeks to days. The ultimate solution was the publication of the Bible of Supply, a massive, 20-volume cross-reference index known as the Standard Nomenclature Lists. This was the tool that finally allowed the mechanic in the field to speak the same language as the clerk in the depot. It grew to over 750,000 entries by 1945, with 32,000 sets distributed globally. This transformed the supply chain from a chaotic guessing game into a standardized system. It meant that when a requisition was filed in a combat zone, the system could actually find the iron. The numbers racket was finally broken by a stack of punch cards and a standardized list. The machine finally learned to speak. By the summer of 1944, the global struggle had become what many logistics officers called a gasoline engine conflict. The victory was no longer just about who could fire the most shells, but who could move them the fastest across a broken continent. The ratio of trucks to men had shifted from 1 to 40 in the previous world conflict to 1 to 4. This was a struggle measured in rubber tires, internal combustion, and the ability to maintain a fleet of 3 million vehicles. To understand how this fleet was built, we must look past the giant factories and into the small, specialized workshops. The war now ran on rubber tires. This is where the slot machine machinist becomes essential. Before the hostilities, he spent his days building coin-operated mechanisms for casinos. Now, he is hunched over a lathe in a small shop, recalibrating his civilian tools to manufacture precision-firing pins and truck axles. He is part of a fragile web of subcontractors, toy makers, car bumper manufacturers, and even piano builders who were suddenly tasked with producing the specialized components that the automotive giants could not make fast enough. One firm, National Slug Rejectors, went from making coin-handling parts to producing heavy-duty axles for tactical vehicles. These small firms were the critical bottleneck of the entire war effort. If one shop in Indiana failed to deliver a specific gear, the entire assembly line in Detroit ground to a halt. The slot machine shop saved the tank. Consider what this meant for the men at the front. The logistical backbone of the liberation of France was not the railroad, but a fleet of thousands of trucks. This was the Red Ball Express. The rail lines had been systematically destroyed by Allied bombing and retreating forces, leaving the military with no way to move supplies to the advancing front lines. This forced the move to a purely automotive supply line. A Red Ball driver was no longer just a chauffeur. He was a critical component of the offensive. He would stay behind the wheel for 48 hours at a time, white-knuckling the steering wheel through a 2-day shift to deliver shells before the artillery lines ran dry. He pushed his 2.5-ton truck through bombed-out villages and over temporary bridges, knowing that if he stopped, the advance stopped. The driver was the engine of victory. The mechanical strain on this equipment was absolute. These trucks were being driven into the ground, overloaded and raced until they literally disintegrated. By June of 1944, the shortage of heavy truck parts had reached a crisis point. To fix this, the planners in the supply branch implemented what they called Special Directives Treatment. This was a high-stakes policy shift that granted truck parts, specifically axles and transmissions, the same priority status as landing craft and heavy artillery. It allowed these mundane logistical components to jump the queue for raw materials. It was a realization that a truck was just as lethal a weapon as a tank. Without the truck, the tank had no fuel. The truck was now a primary weapon. The American industry was forced to pivot once again. The production schedule for heavy trucks was suddenly doubled, a requirement that carried the same industrial weight as building 14,000 medium tanks. Because heavy-duty axles were the primary limiting factor, officials even considered powering trucks with multiple small engines hitched in tandem to bypass the shortage of large power plants. A spring and bumper company spent 12 months retooling its entire operation just to produce driving axles. This was the reality of the industrial grind, a constant negotiation between factory capacity and the ambitious goals of the high command. The success of this mobility did not come from a single breakthrough. It came from thousands of small firms that abandoned their civilian blueprints to build a mechanic civilization on wheels. By the time the convoys reached the border, the system had proven that the ability to move was the ultimate advantage. The machine shop on wheels had won. By 1942, the American industrial machine had achieved what many thought was impossible. It was churning out small arms ammunition at a rate that eventually overshot even the most brutal requirements of the war. But this limitless production model, driven by political pressure from the White House and desperate pleas from the British, created a new crisis. In the rush to meet staggering quotas, the military had accidentally traded reliability for volume. To understand how high the stakes had become, you have to look at the reality of a massive facility like the St. Louis plant. This was a city of 40,000 workers spread across 300 acres, operating in a constant 24-hour cycle. A single production line was calibrated to output 250,000 rounds of ammunition every day. Inside that frantic environment, a dangerous friction had developed between the speed of the line and the safety of the soldier. On the morning of January 4, 1943, this tension exploded into the public consciousness. A local headline broke the scandal of defective ammunition, triggering a deluge of federal investigators. The charges were that inspectors were being pressured to ignore microscopic flaws in cases and loose bullets just to keep the numbers up. A St. Louis inspector is caught in the middle of this high-pressure landscape. She is sifting through a mountain of .50 caliber brass, searching for the one defective primer that could jam a pilot's guns in the middle of a dogfight. She uses magnifying glasses and mirrors, struggling against a foreman who is pushing her to force the gauges to pass subpar ammunition. To her, a rejected round is a failure of the quota. To the man in the cockpit, an accepted round with a flaw is a death sentence. This was the low ebb of morale, where the workers realized that the quality of their mercy was being sacrificed for the speed of the machine. The Ordnance Department was attempting to manage a global supply chain where a single defective round could destroy an aircraft in flight. They realized they could not inspect every single component of every rifle or shell without stalling the entire war effort. They were fighting a war against friction and ineffectiveness. To solve this, the department was forced to abandon the traditional eyeball test and the craftsman's mindset of 100% inspection. They pivoted instead to a new mathematical science known as statistical quality control. To understand why this mattered, you have to see it as a transition from the physical to the abstract. Instead of checking every bullet, they began using control charts to monitor the manufacturing process itself. By 1942, the military held massive conferences to teach this new math to hundreds of officers and civilians. They found that by using statistical sampling, they could actually increase reliability while reducing testing by 2/3. For a consistent manufacturer, this saved enough armor plate to build 30 additional medium tanks every month. The military became a department of statisticians. But even a perfect bullet is useless if it arrives at the front in what soldiers called frontline squalor. This is the part of the logistics story that is often overlooked. The packaging. For the first 2 years of the war, ammunition was shipped in heavy wooden crates that weighed over 100 pounds. These were too heavy for a single soldier to carry and were easily ruined by the tropical fungus of the Pacific or the salt spray of a long voyage. The army discovered that their war reserve was rotting in the box. Waxed fiberboard liners were failing, leaving ammunition corroded and ruined before it ever reached a weapon. This forced a total redesign of the supply chain, shifting to what were called functional assemblies. By 1944, the military introduced the coffee can hermetic seal. This was a steel container with a key opener, designed to keep the powder dry in the most extreme environments on Earth. It was a realization that the container was a piece of ordnance in its own right. They moved toward specialized packaging that allowed a soldier to open a single manageable unit of ammunition that was ready for immediate use. This brings us to the ultimate judge of the system, the pilot returning to base with his guns silent because of a jam, or the infantryman struggling with a corroded belt in a foxhole. The transition to hermetic seals and statistical sampling meant that by the end of the war, the American soldier possessed the most reliable ammunition in history. The department had learned a cold industrial lesson. They had found that in a global war, you cannot rely on the individual eye of an inspector to catch every flaw. You have to build the quality into the process itself. By 1945, the packaging of a bullet was as critical as the bullet itself. It was that simple. Now return with me to that night in late 1944, back to the field mechanic kneeling in the freezing mud of the Ardennes. To understand why he is there, you have to realize that the just-in-time supply chain was finally hitting the reality of a winter counteroffensive. The German surge through the forest had burned through ammunition and fuel at a rate that no one in Washington had predicted. The army was moving faster than its own paperwork could follow, and for a moment, the entire industrial machine seemed to be stuttering. This was the artillery crisis. By late 1944, the expenditure of heavy shells had outpaced all estimates. It was not that the factories had stopped, it was that the perishability of the material was catching up. Ammunition is a delicate chemical compound, and after 2 years in tropical storage or damp European depots, primers were becoming unreliable. The military was facing a frantic scramble to replace their own stockpiles, even as they were being fired. Think about what this meant for the men in the tanks.